Lecture 50, Understanding the Lorentz Transformations. So the first thing I'm going to do is write the Lorentz transformations up here. I'll write the transformations and their inverse transformations for reference. How do we remember how to write the transformations? Well, we imagine a moving reference frame, right, moving with some velocity v, right, and we wonder, well, what's the, we'll call this, the prime reference frame, and we wonder, well, how do we figure this out? Well, if we want to know what the measurements are in the prime measurement frame, right, it's going to be the same, and this is just Galilean, okay? It's going to be the same as the stationary reference frame, but you're going to have to take into account this little distance here, v times t. So the x prime position under a Galilean transformation will be the x position minus vt, okay? So minus this distance, right, so that you get the distance in here. So if you remember that, then you can construct or write the Lorentz transformations like this. So we'd say that x prime is equal to the gamma times x minus vt. See, there's the minus vt that we talked about just a second ago. Yeah. And then, of course, the time coordinate is a little bit funny, but it's symmetrical. So it's going to look like this. Gamma times t minus vx. See that? Yeah. And then we have the inverse transforms, which would say x instead of x prime. I'm going to write those in a different color, just because I have the marker here. So we'd write x is equal to gamma times x prime, not minus vt this time, but plus vt, because everything is going in the opposite direction, right? From the point of view of the train, the platform is going that way, right? If you're on the platform and you see the train going this way, then on the train you'll see the platform going in the other direction. So we switch the sign of the velocity, so it goes plus vt, and t prime equals gamma t plus vx. So there are our transforms and our inverse transforms, okay? So in order to crack this Lorentz transformation, understand what the different terms in it mean, that's essentially what we're trying to do today. What does this first term mean? What does this second term mean? How about this one in the time, and the second term in the time? So that's what we're trying to crack right now. And so the first one we're going to look at is the time coordinate here, and we're going to do it by revisiting time dilation, which we explored previously using light clocks. Do you remember the light clock problem? Yeah. Right. So we had from the train frame, you had a light clock whose beams are going up and down like this over a distance d. But from the platform's frame, what they would have seen is something like this, right? They would have seen a light wave going up here and then down here, so that this distance d prime is greater than this distance here. And so we account for this, the fact that the speed of light is constant in both of these, as meaning that these clocks in the train frame must be running slow. So let's look at that from a Minkowski diagram or a space-time diagram and using the Lorentz transformations. So we'll start by just simply, so I'll write time dilation, and we'll draw a space-time diagram as usual. This is the t-axis and this is the x-axis. So this would be for the platform or the stationary frame. So this would be the platform's frame of reference. And now we'll draw in a little dotted line at 45 degrees. That's a light ray coming from the origin at t equals 0. And that's just for reference. And then we can draw in our t prime axis like this, t prime. And if we needed it, we could draw in our x prime axis like this, where the angle subtended is the same on both sides of the light line. Okay? And here's what I want to do. I want to put a clock on this so that, remember that this t prime axis is also the x prime equals 0 axis. So that's the origin for the train. And let's put a clock on there and let's let it tick for some time, and we'll call this t prime at 0. So that's its coordinate, t prime at 0, okay? Okay. And so we want to see what is that time in the platform's frame. Well, we know that x prime is equal to 0 all along here, right? So we're going to use that in the Lorentz transformation. So we're going to solve for t. Oh, I put a prime here. Shouldn't be a prime there. Maybe I should do it in purple since I'm using this one. I'm going to use the inverse transform to see what this time is. Oh, I'm going to mess this up. This should be t prime. This is x prime, right? So that's why they're transformed and inverse transforms of each other. These give you the prime coordinates in terms of the unprimed, and these give you the unprimed coordinates in terms of the prime. And there's a prime missing here too. Goodness. There we go. All right, so we're going to use this equation to figure out what this is in the platform frame. So we'll get t is equal to gamma t prime plus vx prime. But remember, x prime all along here is 0, right? So this goes to 0, and so we get that t equals gamma t prime. T at the origin is equal to 0, and so is t prime. And so for that reason, we can write this as delta t equals gamma delta t prime. Okay? So it's the time interval that has taken place since from the origin, t prime equals 0, to t prime. And so this is a delta t in terms of this delta t prime. And that's just the regular time dilation that we explored previously. And if you look, you see that it corresponds to this term right here. Similarly, if we were to consider the other way around, to look at the inverse transforms, I don't want to get too carried away with the colors here, but since I'm doing an inverse, how would we draw it from the train's perspective? If we put the clock on the platform, right, and ask what the train is saying, from the train's perspective, he is stationary. The platform is moving, but in the opposite direction. So we would make a light line over here at 45 degrees. Here would be the t axis, call this t prime, this x prime, okay? And then we put a point right there, and we would say, oh, okay, well, we've got, this occurs at t equals, some t value, and x is equal to 0 all along there. So we have this value. We would then use this equation, and we come up with the same result. We get t prime equals gamma t. So both the people on the train and the people on the platform see the moving clock as running slow. And if you stop them and said, hey, your clock was running slow, they'd say, no, my clock was running just fine. Your clock was running slow. If you're in that frame, you don't see your clocks running slow. Okay? You only see moving clocks running slow. That's a little hard to process. It's not like if you're on a moving train, it's going really, really fast, that everything is slowed down and you're moving very slowly. You're like, why am I moving so slowly? Everything is normal. But to the outside, the reference frames outside, right, the platform in this case, right, would seem to have slowed down. You'd see them moving slowly. So it's a little funny, but they disagree, and we're going to get to the heart of that disagreement in this lecture. But this is what it would look like if you were going to try to, crack it from the other way around. Now the train frame is stationary and the platform frame is moving, but in the opposite direction. That's why it's going that way. You see?
Yeah.
Okay. All right. That's time dilation. Now, if we want to get to what's going on here, this gamma x prime term, or gamma x term, and this we can get from thinking about length contraction, which is another thing that we talked about previously, but without the aid of space-time diagrams or the Lorentz transformations. So again, we're going to draw the platform frame like this, x and t. We'll draw our little light line. We can put our t prime axis here, and we can put our x prime axis here. But I'm going to label a point on here, and I'm going to draw two world lines. I'm going to draw this world line, the t prime axis, which occurs at x prime equals 0. This is the world line of one end of my measuring rod. Okay? This is a measuring rod on the train. This is, say, the left end of it. Okay? Whereas this point here, we're going to have a world line here as well. It'll be run parallel to this world line. That's a very unstraight line. Let me see if I can fix that. A little better. This world line is also a time axis in the train frame, but this occurs at x prime equals, I'll call it L prime. Okay? So here we have a moving measuring rod in the train. Okay? And so we want to ask the question, what is its length in the platform frame? Okay?
Okay.
So the key to doing this is to remember that distance is something that you measure simultaneously. Okay?
Okay.
You measure two positions, especially if something's moving, right? You want to measure, say, the left end of the rod and the right end of the rod at the same time. Okay?
Okay.
So we want to measure, and we'll say we're going to make the measurement at t equals 0. That's our measurement time. We're in the platform frame, so we use the unprimed clocks, the ones that are sitting still relative to us. So that's when we're going to make the measurement. Now, if I look up here, I've got a t equals 0. So this is the equation we're going to use, and I'll show you why. So let me just write it first. X prime equals gamma x minus vt x prime and x. This will be our L prime, okay? Because we're assuming that the other end of the rod is at the origin.
All right.
Well, if this point here is, I always write the time first. Let me write this out here. And we don't know what the time is in this frame. I'll just write it as t prime for now, comma L prime. So L prime is what we're trying to get at, right? And it'll be equal to, and so x, this will correspond to L, the length that we measure, okay?
Okay.
Minus v times t, but t is 0 in this frame, right? So that term goes away. And so what we get is L prime equals gamma L. Now, usually the way that we like to look at this is we like to solve for L and say that L is equal to L prime over gamma. And the reason why is because this allows us to interpret it properly and make the statement in the usual way. We usually say that moving measuring rods contract. This statement would say that measuring rods are always longest in a stationary frame, right? So in the frame in which the proper length is the frame in which the measuring rods are stationary, okay?
Okay.
The language in this stuff can get really confusing, and so you have to think carefully about how you're saying it. I may have said it all wrong, but I think we're okay. Remember, what I didn't really say what gamma is. Remember that gamma is equal to 1 over the square root of 1 minus v squared. And so for that means that gamma is always greater than or equal to 1. If v is 0, then gamma is 1. Any other value of v, all the values of v are going to be less than 1. So it would be like 1 minus 0.9, because we're saying the speed of light is 1. So our velocities will always be something like 0.6 for 60% the speed of light, 0.8 for 80% the speed of light, right?
Yeah.
And so 1 minus, say, 0.8 is a value which is smaller than 1. And so we'll be dividing 1 by something less than 1, so it's going to get bigger, you see?
Yeah.
So gamma is always greater than or equal to 1. Well, with time dilation, what does that mean, right? That means that delta t is always greater than or equal to delta t prime. So if delta t prime, say, if the train frame says, hey, that was 5 minutes, and the platform would disagree and say, no, your clocks were moving really slowly because I measured a much longer time for you,
Yeah.
right? I observed you, yeah. Well, I can get confused just trying to say the verbiage is tough. Whereas here, right, since gamma is always greater than or equal to 1, that means that the distance that you measure in the platform is always less than what the actual length, what the length of the rod is in the moving frame. So if the rod was, say, 10 feet long on the train, then as it's zipping by, you would observe that it's less than that. It's shorter, okay?
Okay.
Yeah. They contract, okay? So, but this gamma L term, right, is really this part right here. And so we see that this term here and this term here is length contraction, okay? So the leading terms on either the spatial or the temporal part is either time dilation or length contraction. That's what those first terms are. Now we have to get to what are these terms at the end here, the minus Vt, the minus Vx, okay? Okay, so to motivate what comes next, I just want to consider a different problem for a moment, okay? I want to imagine that I'm measuring the length of a train, okay? Here's the train, and it's going to move in this direction with some velocity. It's not necessarily relativistic though, okay?
Okay.
But I've got, as usual on my platform, I have clocks lined up, okay? And so right here, I have an observer who measures that, hey, I see the left end of the train, and at t equals 0. So at t equals 0, the observer right here, at x equals 0, observes the left end of the train. Now, all along the platform, we're going to have people with, so put little tick marks here, people with clocks, like so, okay? Let's put this guy here. And I'm just going to highlight that this is the guy right here at x equals L, and we'll say that the length of this is, say, 10 meters. 10-meter long train. Decent distance. Actually, it's kind of short, but that's fine. And this is the guy that's going to measure the right end of the train at t equals 0. Now you're wondering, well, why isn't this guy located here. That's where the right end of the train is, right? Well, the reason why is because his clock is out of sync. He thinks that it's t equals -2. How about the velocity equal 10 meters per second? Okay? So these two clocks are out of sync. What happens is, so this is at t equals 0 by the origins clock, okay? And at t equals 2 by the origins clock, the train will have, so here's x equals 0 again, rolled along to this point, where now the observer L units away, right, sees the right end, and his clock tells him it's t equals 0. So he's like, okay, time to make the measurement of the train. So I'm the guy along the track that sees the right end of the train when t equals 0, so we're going to say that the right end of the train occurs L meters away from the origin. You see how this is working? It's like we make the measurement, and then we get together and sit down at a table somewhere and we look through our notes. Everybody observes the position of the train as they see when they see it pass by, and we look for the guys who had the left end at t equals 0 and the guys that had the right end at t equals 0, and that's how we calculate the distance of the train. Well, what are we going to get here? Right, because the clocks were not synchronized, this little bit of distance, we're going to overestimate the distance, you see? We're going to say the train's longer than it actually is. Because this distance L, right, has 2 seconds of travel. So that's what is, 10 meters per second times 2 seconds is equal to 20 meters, right? So we're going to get that the train is 20 meters longer than it actually is. And this is solely because of our clock synchronization problem, okay?
Okay.
And so that turns out to be at the heart of relativity paradoxes, is the relativity of simultaneity, it's called. So now we'll go back to relativity. The point of that, though, is to see how clocks not being synchronized can affect length measurements. Okay?
Okay.
And I think was that clear? Does everyone understand that example? So let's consider, I'm going to put some 3 clocks here on the train and 3 clocks on the platform. This point here is going to be x equals x prime equals 0. Now, I'm going to set the clock time on the platform equal to 12 o'clock exactly. Okay? And in the usual way, these guys are going to all synchronize the clocks using the Einstein synchronization convention. They'll all say 12 o'clock as well. You see that?
Yeah.
So all the clocks on the platform say 12 o'clock. Now, on the train, they're doing the same thing. Okay? So at least we know, because we've agreed that our clocks are going to be set to the same time at the origins of our reference frames. This clock will say 12 o'clock at the same time this clock says 12 o'clock when they're both at the same position, x equals x prime equals 0. Okay?
Okay.
What about these times? Okay? So we'll call this position here x equals, I want to write that a little bigger. I tend to write really small. I want to write bigger. X equals minus L, and this rightmost clock is going to be at x equals plus L. Now we have a value of x and a value of the time. So x equals L, t equals 0. X equals L, t equals 0. See how we can use this equation, this Lorentz transformation equation, to see what t prime is? So what is t prime? T prime will be equal to gamma times t, which is 0, minus vx, right? So that would be minus vl. So this time is equal to minus gamma vl. Seems like I made an error here. Hang on a second. Of course, my error is x is minus l, so it's minus v times minus l. So this should become plus, right? Since this length measurement is at minus l, minus v times minus l is positive vl. Got it?
Yeah.
So what does that look like on the clock? It looks like this. The clock is ahead in time. Okay?
Okay.
Now let's look over here at x equals L. So the same thing as before. We'll evaluate t prime equals gamma times t, which is 0, right? All along here. T is 0, and so we'll have minus VL. This time it'll stay minus VL. So here t prime is equal to minus gamma VL. So here the clock is running behind. Okay? Does everyone see how I got these? I used the Lorentz transformations to consider what the time on the train is, right? For t equals 0, x equals minus L. It's just simply plugging it into the appropriate Lorentz transformation equation, and you get that t prime equals gamma VL. Okay?
Okay.
And for x equals L, t equals 0, that's this point right here, t prime is equal to minus gamma VL. Okay?
Okay.
Now I'll do a nice space-time diagram to see what that means or how to interpret that. Start with my t prime axis or my x-axis and my t-axis here. And I'm going to extend this out in this direction into the minus x territory and then into the minus t territory, okay? Now I'm going to put my light line in here. I think that looks roughly like... Now I'm going to put in my t prime axis, the one that goes through the origin. But I'm also going to point out that we're going to have some distance. We have minus L and plus L. And I'm going to make... Well, first I have to draw my x prime axes. So you have t prime, I've got x prime. I really should have drawn t prime in a different color. Let me see if I can... There. You get all these lines crisscrossing, it can get confusing. But in addition to this x prime line that I've drawn here, this is at t prime equals 0, remember. T prime equals 0, right? I'm going to draw parallel lines to that. This is just basically the x prime axis at different times. Try my best to make them look parallel and also go through the same point. That looks pretty good. Okay, I think we have what we need. This is at minus L prime. I just relabel that minus L prime. This is at positive L prime. So the clocks on this x prime axis where t prime is equal to 0, it looks confusing the way I've drawn it. These are the ones that say 12 o'clock everywhere. All along here, these clocks are going to say 12 o'clock because this is t prime equals 0. This is the x prime axis for the train at a different time though, right? If you look, where does it intersect its time axis? It's negative, right? So this is a negative number. So this is t prime equals, and we know from what we just calculated a minute ago, this is going to be minus gamma v, whoops, minus gamma vl. I should write that bigger. T prime equals minus gamma vl. That's this line here. Why is it minus? Well, see where it intersects here? So this is where all of the clocks, this line of simultaneity, right, is looking kind of back in time, right? It's before. That's the before, you see?
Yeah.
Remember, lines of simultaneity in the platform frame are just here and here and here, right? So if I pick any point through here, these are all different x positions where t is equal to whatever that distance is, right?
Yeah.
So all these are is the same thing, but for the train frame. And now let's look at this, this line above here. What is this? Well, this corresponds to minus L, right? And where does it hit the t prime axis? Here. That's after t equals 0, or t prime equals 0, you see?
Yeah.
So this is where all the clocks are a little ahead. They're at a later time. I always get mixed up whether it's ahead or behind, but that's fine. So here the clocks look like this, okay? They're showing a later time. Does that make sense? And so this is where, this is the x prime axis where t prime is equal to positive gamma vl. So the left side of the train, remember the clock there was at a later time, after t prime equals 0. The origin, of course, is t prime and t are both equal to 0 because they've agreed to synchronize each other, the clocks at that point, okay? But you can only do it at one point. So it's probably an interesting question for you to go home and ask yourselves why that is. But and the right side of the train, right? So I'll put the train back up now that we have some room. Here's the train, right? And we found that the clock in the center of the train, which we agreed was our origin, so it's synchronized. It has the same time as the clock on the platform. They've agreed to, when their origins cross, they sync up at t equals 0. But this clock on the right-hand side, right, is before t equals 0. And the clock on the left-hand side of the train is at a time after t equals 0. Okay?
Okay.
And this is how we can pictorially understand that. Now, this is called the relativity of simultaneity. And it basically says that there's a synchronization issue, a delta t we'll call it, which is equal to gamma v x. And then technically we'll put it over c squared if you want to use units where c is not equal to 1. Okay?
Okay.
To get the units right. And that corresponds to this last term we see here. See this term?
Yeah.
The vx prime and the minus vx, right? That's the synchronization of the clocks, okay? And understanding a lot of problems in relativity come down to the relativity of simultaneity because the clocks aren't synchronized. It's similar to the example that we talked about before where our clocks are not synchronized and we tried to measure the length of a train that rolled by. right?
Yeah.
Not relativistic train, just a slowly moving train. But if our clocks aren't synchronized and we get back together and try to put together what's the length of the train based on our observations, we get it wrong. And that's the reason that you get these weird observations for time dilation and length contraction in relativity. It's because of the synchronization of the clocks. Okay?
Okay.
Yeah, well, we'll use this to our advantage when we talk about the twin paradox, which I think we might do in the next lesson. Yeah, I think we will. Probably do the twin paradox next because it's fun. But yeah, it takes some processing to think about this and make it stick. And I just realized I don't understand fully what this last term is. This term here, that is something, and then it'll be this term here in this equation. The Vx prime and the minus Vx term are relativity of simultaneity. I'm not sure what this term is, so I don't know about that. I'll look into it. Okay, I think that's all. Yeah, that's all I was going to say. Make sure I got it right. Now you guys, I guess you could call this L, right? The farther away the clock is, the more out of sync it is. Okay.
Okay.
So it's rare that we don't understand this stuff because it's not part of human or even animal experience. We're not used to dealing with things that move past us at speeds close to the speed of light. So our evolution, our DNA doesn't have that kind of physics in our head like we do with the physics that we do know. Right? Most of the physics that we talk about in classical mechanics, for example, is stuff that all animals know. Right? They know how to push things and make them fall over. It's just built into us naturally. We already know it. This we don't know naturally. There's no reason for us to. So it's just not something that's hardwired in our brains. So it seems weird and strange to us. And that's why this seems weird and strange to us. Because we don't have any experience with things that are traveling close to the speed of light. Anyway, that's all I was going to say about that. Okay, next time we'll talk about the twin paradox.